In the annals of modern history, no single device has altered the course of human behavior, communication, and commerce more than the smartphone. And among smartphones, the iPhone stands as the monolithic standard of design and engineering. But behind the sleek glass and cold metal lies a manufacturing process so complex, so vast, and so secretive that it rivals the Manhattan Project. To hold an iPhone is to hold the culmination of human material science. It is a device composed of elements from every continent, assembled by the most advanced robotics on the planet, and powered by a brain built on the edge of quantum physics. Welcome to the iPhone City in Zhangzhou, China, and the TSMC foundries in Taiwan, the fortresses where the future is forged. Our journey begins at the atomic level with the creation of the processor, the A-series bionic chip. This is the most expensive and difficult component to manufacture. It starts not in a factory, but in a sand mine. Silica sand is purified and melted to grow a single perfect crystal of silicon, a bowl. This crystal, shaped like a massive cylinder, is sliced into wafers thinner than a human hair and polished to a mirror finish. These wafers are shipped to the fabrication plant, or fab. This is the cleanest place on Earth. The air in a hospital operating room contains about 10,000 particles per cubic foot. The air in a Class 1 clean room contains 0. Workers are covered head to toe in bunny suits because a single flake of human skin or a speck of dust falling on a wafer would destroy the circuitry like a meteor hitting a city. The manufacturing process, known as photolithography, involves using extreme ultraviolet light. This light is generated by firing high-power lasers at droplets of molten tin, creating a plasma that emits light with a wavelength of just 13.5 nanometers. This light is projected through a blueprint mask onto the silicon wafer. It etches billions of transistors on a chip the size of a fingernail. We are talking about structures that are only 3 nanometers wide. That is the width of a few DNA strands. We are writing with light on the scale of atoms. Layers of copper and other conductive metals are vapor deposited onto the silicon to wire these billions of transistors together. It takes months for a single wafer to complete the journey through hundreds of steps. Once finished, the wafer is sliced by diamond saws into individual chips. Each chip is a supercomputer ready to be the brain of the device. While the brain is born in silence, the body of the phone is born in noise. The chassis of a modern iPhone is a marvel of metallurgy. It starts as a solid block of aerospace-grade aluminum, 7000 series, or surgical-grade stainless steel. These alloys are custom formulated by Apple metallurgists to be harder and more rigid than standard metals. The solid blocks enter a massive hall filled with CNC, computer numerical control, machines. These milling machines, spinning at 30,000 RPM, carve the phone's unibody from the solid block. It is a process of subtractive manufacturing, removing everything that isn't an iPhone. The machining tolerances are measured in microns. The drills carve out the complex internal geometry where the battery and logic board will sit. They drill the speaker holes, which are not just holes, but acoustically tuned chambers. Once machined, the raw metal skeleton is rough and sharp. It must be refined. The chassis goes through a rigorous polishing process, often involving being tumbled in vats of ceramic media or buffed by high-speed robotic arms until the metal is flawlessly smooth. Then comes the color. Paint would chip and scratch, so the metal undergoes anodization for aluminum or PVD for steel. In anodizing, the chassis is submerged in an acid bath, and an electrical current is passed through it. This oxidizes the surface, creating a microscopic honeycomb structure in the metal itself. Dye is then injected into these honeycombs, and the pores are sealed. The color becomes part of the metal's molecular structure. For the Pro models using stainless steel, the PVD process vaporizes solid metal in a vacuum chamber, blasting it onto the phone's surface to create a coating that is harder than the steel itself. Simultaneously, in another part of the Gigafactory, the logic board, the nervous system, is being assembled. This is surface mount technology at its peak. The printed circuit board, a multi-layered sandwich of copper and fiberglass, enters the line. A machine prints solder paste onto the board, then pick-and-place robots, moving so fast they are a blur to the human eye, grab thousands of tiny components, capacitors, resistors, memory chips, and the A-series processor, and place them onto the board. The speed is dizzying. Tens of thousands of components are placed per hour. The board then travels through a reflow oven. The heat melts the solder paste, fusing the components to the board. But the inspection is rigorous. Automated optical inspection machines use cameras and X-rays to look under the chips, ensuring every single solder ball has melted correctly. A bad connection here means a dead phone. The density of components is insane. Engineers fight for every millimeter of space. This logic board is a dense city of electronics that will process every photo, every message, and every thought the user has. The battery is another critical component. It is a lithium-ion polymer pouch. Unlike the cylindrical batteries in a Tesla, these are flat and often L-shaped to fill every nook and cranny of the chassis. Robots apply adhesive pull tabs to the battery, a design feature allowing for future replacement and recycling. The battery is pressed into the chassis with exact force. At this stage, we have a brain, a body, and a heart, but the device is still blind and mute. It needs its senses. We now move to the clean room assembly, where the most delicate components are integrated. The camera system is the defining feature of the modern smartphone, and assembling it is a feat of optical engineering. The camera module is not one lens. It is a stack of 7 or 8 precision-ground plastic and glass elements aligned perfectly over a massive image sensor. This stack is suspended on tiny springs and electromagnets. This is the OIS, Optical Image Stabilization and Sensor Shift technology. It allows the lens or sensor to physically float and move hundreds of times per second to counteract the shaking of your hand. Building this module requires robots with force sensors capable of detecting the weight of a feather. Dust is the ultimate enemy here. The assembly happens in a hyper-clean environment where the air is filtered constantly. A single microscopic dust particle landing on the sensor would result in a permanent black spot on every photo taken by that phone. The lens assembly is sealed and then mated to the image sensor using active alignment, where the camera is turned on and focused by a robot while the glue is still wet, to ensure perfect sharpness across the frame. The screen, the window into the digital world, is prepared next. This is not just glass, it is ceramic shield. Apple works with Corning to create a material that is a hybrid of glass and ceramic crystals. The glass sheets are bathed in a molten salt bath of potassium nitrate at 400 degrees Celsius. In this chemical exchange, smaller sodium ions leave the glass and larger potassium ions take their place. These larger ions wedge themselves into the glass surface, creating a state of high compression. This tension makes the glass incredibly tough and resistant to shattering. The OLED panel is laminated to this glass in a vacuum chamber to prevent bubbles. Now the marriage happens. The screen is connected to the chassis, but before it is sealed, a robot applies a precise bead of waterproof adhesive around the rim. This glue, combined with silicone gaskets on every button and port, gives the phone its IP68 water resistance rating. Robots press the screen onto the body with calculated pressure to activate the adhesive. Finally, two tiny pentalobe screws, proprietary tamper-resistant screws smaller than a grain of rice, are driven into the bottom of the phone by electric screwdrivers that measure the torque to the exact Newton meter. The phone is physically complete, a sealed slab of glass and metal, but it is a blank slate. It enters the provisioning racks. Imagine a wall of thousands of iPhones plugged in simultaneously. The Apple logo flashes on the screen for the first time as the iOS software is injected. This is the first heartbeat. The operating system wakes up the hardware. The phones then undergo a grueling automated test suite. The screen flashes red, green, blue to check for dead pixels. The speakers play frequency sweeps to test the audio range. The haptic engine vibrates. The cameras take photos of test charts to verify focus and color accuracy. Then comes the torture. Random samples from the production line are taken to the reliability lab. Here, robots drop phones onto concrete from different heights. They are tumbled in metal drums to simulate being loose in a bag. They are sprayed with jets of water and submerged in tanks to test the seals. They are placed in ovens and freezers to ensure they work in the Sahara and the Arctic. Machines press the buttons hundreds of thousands of times to test their lifespan. If a batch fails, the entire production line is halted until the root cause is found. Once passed, the phone moves to the packaging line. This is the final stage of the user experience design. The screen is covered with a protective paper sheet. Apple has removed almost all plastic from the box. The phone is placed into the iconic white box. The engineering of this box is obsessive. The friction of the lid is calibrated so that when you hold the top, the bottom part slides out slowly, taking exactly 3 seconds to drop. This whoosh effect creates a moment of anticipation for the buyer. The charging cable is coiled in a perfect circle. The documentation is tucked away. The boxes are wrapped, palletized, and shrink-wrapped. Security in the shipping area is tighter than a bank vault. These pallets are loaded onto unmarked trucks and driven to airports. Chartered Boeing 747 freighters filled with nothing but iPhones take off from China, heading to distribution hubs in Alaska, Kentucky, and Europe. It is a logistical ballet that moves millions of units in days. When a customer walks into a store and peels the paper seal off the box, they're touching the end result of a global supply chain that spans mines in Africa, foundries in Taiwan, and assembly lines in China. They're holding a device built by robots, refined by lasers, and powered by quantum physics. It is the most sophisticated consumer object in history, yet it feels as natural as a polished stone. This is the magic of modern manufacturing, making the impossible feel effortless.